Share. All right, can you see the slide on the screen?
Yes, doctor.
Okay, thank you. Right, in our previous class, we have discussed about the formation of PN junction. Okay, and we learned that in order to form a PN junction, we have to bring a P-type semiconductor material on one side and an N-type semiconductor material on the other side together, right, to form a metallurgical interface, right? An interface where you have your contacts, a contact of P and N semiconductor materials, and upon joining together as a junction, we have learned that there will be a diffusion of majority carriers electrons from the N-type into P-type, holes from P-type into N-type upon the formation of concentration gradient at a junction. And we learned that the diffusion of the majority carriers only take place near the junction region, not the overall, not throughout the overall P-type or not throughout the overall N-type material. And as far as the band diagram is concerned, when we have two different materials, you have learned that the Fermi level of the P-type material is close to the EV, and the Fermi level of the N-type material is close to the EC. And upon the combination, upon joining with each other to form a junction, we are going to have a single Fermi level eventually at thermal equilibrium condition because of the alignment of each EF from both sides to form a single level, right? So this is what we saw from the previous class, right? So if you want to look at the Fermi level again, for example, then you can see here the Fermi level of the P-type on the left is close to the VB, and the one on the right for N-type is close to the EC. And then upon the combination or upon joining with each other, we're going to have eventually a single EF at thermal equilibrium condition, right? And we have also discussed a couple of times that the majority carriers in a P-type semiconductor material is given by PP0 or Na, and therefore the minority carriers will be given by the law of mass action, Ni squared over Na in this case, or Ni squared over PP0, same thing. And the same is also true for the N-type material, where your majority carriers are electrons, and that's given by Nd or equals to Nn naught, and therefore your minority carriers, the holes are given by Ni squared over Nd or Ni squared over Nn naught. All right, so those are already learned in the previous class, and we have also learned about this carrier transport, if you like, of both carriers at a junction region, which involve both drift and diffusion of electrons, as stated on the slide, and also drift and diffusion of holes, which is given by the blue particles, right? So you should be able to sketch for yourself, as I said in the previous class, how does a band diagram of the P-type and N-type material looks like before the formation of PN junction and after the formation of PN junction, where you need to incorporate the banding in the middle in order to accommodate the single EF at thermal equilibrium condition, right? So we've also learned that when you have a single Fermi level, or when you have achieved the thermal equilibrium condition, there will be these very high, right, QVBI, which is initiated by the formation of the PN junction. And if you want to do the calculation of this very high, if you wanted to save this, how electrons and holes drift in thermal equilibrium, because I thought majority carriers drift only when electric field is applied. Yes. Okay. Yes. The drift component only exists. The drift component only exists when you have electric field applied. In this case, you have to bear in mind that the moment you have your PN junction form, there will be internal or built-in electric field form at the junction. So in this case, the field is not applied externally, but rather it's formed by the built-in electric field upon the formation of the junction. So remember, why do we have the field? So we have the electric field present near the junction region because of the formation of the fixed ion charges near the junction. So remember last time we talked about whenever you have on the p-type material, which is positive in nature, so upon the diffusion of the holes into n-type, so you are going to have fixed ion charges which are negatively charged near the junction region. On the other hand, you're going to have positive fixed ion charges in the n-type near the junction region. And this, the presence of the negative and the positive ion charges, fixed ion charges near the junction will create electric field. And this is called built-in electric field, and it affects the drift of the carriers near the junction. Okay? Yes, due to internal electric field rather than external electric field. So when it comes to the drift component and electric field, it doesn't have to be necessarily external in nature. It can also be internal in nature. As long as you have the field near the region or applied to the material, you're going to have drift component. But in this case, we're talking about internal electric field, right? Okay. Right, good question. So we have stopped at the formation of the Berry height, which has to be overcome by the carriers in order to further diffuse. But they are now stopped from diffusion due to the presence of the Berry height, just like the table we discussed last time. And that the Berry height, this Q psi naught or QVBI, if you like, you can replace this with VBI, is given by, if you go back to this page, the EG is given by the difference between EC and EV. And if you want to know the barrier height, you can just take your EG minus your E1 and minus your E2, and then you're going to have your QVBI already, right? From the space given there in the band gap. So your QVBI is given by EG minus E1 minus E2, and E1 and E2 is essentially EF minus EV. If you remember last time we talked about EF minus EV, EC minus EF, and you have already learned the equations, and they are given by this KT ln NV over NA minus KT ln NC over ND, right? And this can be simplified to come to this equation, which gives you VBI equals to VT thermal voltage, 26 millivolt, ln NA and NA times ND over NI squared. So NA being the doping level for the p-type, ND is doping concentration or doping level for the n-type, and intrinsic carrier concentration squared. And you can also write this equation as the equation below. Thermal voltage ln NA, you can replace that by PP naught. Okay, NA is PP naught, and ND over NS squared is essentially 1 over PN naught, or you can just write PN naught down there. So therefore, you're going to get VT ln PP naught over PN naught, right? Majority carriers in the P-type over minority carriers in the N-type, right? Minority carriers. Remember the three things that you have to mention. For example, the first one up here is density of holes in P-type material at thermal equilibrium over density of holes in N-type material at thermal equilibrium, right? So density of holes in in the P-type over N-type, and that is also equal to VT ln NN naught over NP naught. So the inverse of this, okay? The bracket component is actually the inverse of this, and the rest is just the same thing. So take this equation to the next page. So the equation is this, as we discussed. And if you rearrange this equation, you will get Pn naught. For example, if you want to calculate the minority carrier concentration, why do you want to know the minority here? Because when you have the P and N type, say this P type, this N type combined together, and you're going to have holes diffusing from the P type into N type. Holes are the majority carriers in the P type, but the moment they have crossed the junction, the border, the moment they have reached into N-type material, now the holes are the minority carriers. Okay, and the same is applicable to the electrons as well. Electrons are majority carriers in the N-type, and upon diffusion, upon the crossing of the junction, electrons become minority carriers in the P-type. Holes, minority carriers in the N-type. So that's why we need to calculate the level of the carriers in the when they are the minority carriers. So that means you want to know the holes in N-type, and you also want to know the electrons in P-type. So that's why you need to rearrange this equation from the above equation to be able to calculate the minority carrier level at thermal equilibrium. And therefore, that's going to bring you to Pn naught. You can just rearrange this. Pn naught is equal to Pp naught exponential of negative q VBI over KT, and the same is also true for NP naught, right? So NP naught is equal to NN naught exponential of negative q VBI over KT. So here, recall the three things. That's why it's important, even though it's very basic. You have to be able to tell yourself what's the meaning of this. Density of holes in N-type material at thermal equilibrium, which is calculated when the holes became minority carriers in N-type material upon crossing the junction. And the same is also true for N-type. Density of electrons in P-type at thermal equilibrium, right? So you can graphically represent this by looking at the below graph. If you plot them in terms of ln N or ln P on the y-axis, and then x-axis is the distance across the P junction and N. So they are totally P-N junction. So the left-hand side is the P-type material. Left-hand side is the P-type material. So this whole thing is P-type material, if you like. And this whole thing is the N-type material. So upon combination, you're going to get fixed charge region in the middle, which is also called space charge region or depletion region, and that's given by this dotted line on the left and on the right. So in the middle there is the depletion region, which consists of the fixed ion charges. Okay, and to relate to this equation, the original doping level in the p-type on the left is given by pp naught or equals to Na, as we discussed a long time ago. And on the left here is where your holes are the majority carriers. So the moment the holes cross the junction, you can represent this by a drop in this profile. And now the holes on the left, this Pn naught, are the holes on the right in the N-type. Now is labeled as Pn naught, holes in N-type at thermal equilibrium. So holes are now the minority carriers, and that's given by Ni squared over Nd. Okay, Nd no longer Na, because now the holes are sitting inside N-type material. Okay, and the same goes for N-type as well. So the N-type is the majority electrons, the majority carriers in the N-type materials, and the concentration is given by Nn naught equals to Nd. And the moment the electrons have crossed the junction into the p-type, the electrons are now the minority carriers. So Np naught, minority carrier of electron in p-type material at thermal equilibrium, and it's given by Ni squared over Na, right? No longer Nd, because now the holes are within the p-type material. Okay, so is it okay? Can you understand this graph for now? Okay, anyone couldn't understand this? Can tell me now, I can repeat. So you can just sketch this line This line, for example, it starts from holes being majority carriers. So we assume constant doping level in p-type, and then it's crossing the junction region, and then it drops because now it becomes minority carriers. And the level is given by Pn naught instead of Pp naught. And the same thing you can do for electron as well. It starts off with uniform doping level within n-type material, SNN naught or ND, and then they diffuse across the junction, and then they become minority carriers, and they are represented by NP naught, Ni squared. Okay, so you have to get this clear first, because this is the thermal equilibrium condition before we do anything else to the system, before we do anything else to the junction. So next, we're going to do something to the junction in terms of application of bias, application of illumination of light that will alter the level of the carriers within the PN junction, right? So you have to get this clear first, because this is thermal equilibrium condition. From this formation, you can also plot space charge density. So space charge density is what sits in this region, yeah? This region consists of positive and negative charges. You can represent them as this, okay? They are of equal area but opposite polarity. So the positive charges here is reflecting the n-type material, because it has lost electron as a majority carriers, leaving positive charges fixed. And the same thing happens to the p-type material as well. It has lost holes as majority carriers, leaving fixed negative ion charges. And these Q and D or Q and A just represent the magnitude of the charge on either side, positive and negative, right? So they are not mobile ions, they are immobile ions. Depletion approximation at a junction. In the space charge region, the carrier densities N and P are assumed to be negligible compared to Na and Nd. Na and Nd is way outside. Outside the depletion region, the space charge is considered to be zero. Okay, outside this region. So if you take this region, for example, so you only have fixed ion charges in this middle region. Kat sini je ada positive and negative. So this positive and negative here is actually positive here on the right, negative here on the left. So this is the only region where you have these charges. So luar pada tu, you can see that the level goes off to zero, right? It reduces to zero. So that means that means outside this region, to the right of this and to the left of this, the charge is zero. The charge is equal to zero. But it approaches neutral condition as it goes away from the junction, right? So you can still represent this as this, just like what you saw on the previous page. Same thing, positive ion charges, negative ion charges. Therefore, positive ion charges, negative ion charges. Q and D on the right, Q and A on the left. And this is the Poisson equation to represent the electric field at the junction. And this is the barrier height of the junction. So let's try this equation that we have summarized on this page, right? VBI equals to VT ln NAND of Ni squared. So let's just try this simple calculation as an example. So consider a silicon PN junction at T equals to 300 Kelvin with doping concentration of Na 2 times 10 to the 17 per centimeter cube and Nd equals 10 to the 15. So P type equals to 2 times 10 to the 17, N type equals to 10 to the 15. Calculate the built-in potential barrier at this junction. So the VBI, well, you can assume either your Ni equals to 1.5, 10 to the 10, or 1.0 times 10 to the 10. Either one is fine, as long as you're consistent in the calculation throughout. So for example, if you want to use 1.5 times 10 to the 10, you can just plug in the equation. VBI equals to VT ln Na times Nd over Ni squared. Vt is already known, ln Na and Nd are given, Ni is given, therefore your VBI is going to be 0.713 volts, right? So is it okay for this calculation? Is it straightforward? Any question on this? Ada? Good, right? Simple, right? It's just plugging into this equation, right? Thermal voltage ln NA/ND over NS squared. Right, so let's move on to the next one, space charge width or depletion region width. Same thing. If you encounter a space charge region or depletion region, same thing, right? So the definition of this space charge width is actually the distance that the space charge region extends into the p-type region and n-type region from the junction, from the border, if you like. So also called depletion region width. Okay. So for example, if you take your p-type material on the left, n-type materials on the right, and this red and blue curve are just the plot of your majority and minority carriers like this, right? Just now. And then we have fixed ion charges in the middle near the junction, negative for the p-type, positive for the n-type. And then you have neutral region further into p-type, neutral region further into n-type, but you only have space charge region right across, right near the junction. Okay, remember last time we talked about this, these areas, and also these areas is actually referring to these areas. Okay, these areas. So that means outside this region to the left, outside the region, this region to the right, you can assume that both p-type and n-type are neutral in nature. There is no space charge at all. Okay, and then you have the depletion region width. So this depletion region width is given by the width of depletion region into the n-type material to the right, and depletion region into the p-type material. So essentially, if you combine xn and xp, xn plus xp, you are going to get the whole width of your depletion region or space charge region here in the middle. So this region here, the whole width is given by xn plus xp, right? And each, you can see the equation here is given by this equation, okay, times the VBI over Q, then doping level, right? The total depletion region or space charge width W is the sum of the two component xn plus xp. And W can be further summarized into this. You can either use this equation or you can use each and combine. Either one is fine, right? This one is obviously a lot easier because you just have to do a single calculation, right? Right, so let's try another calculation to demonstrate this. Consider a silicon p-n junction at T equals to 300 Kelvin with doping concentration of Na 10 to the 16, Nd 10 to the 15. Calculate the space charge width of this junction for zero bias condition. What does it mean by zero bias condition? What does it imply? Zero bias condition. There's no bias, therefore, you can also call that as what condition? Thermal equilibrium, yes. There is no bias applied, there is no illumination applied, therefore it is under thermal equilibrium condition. Okay, so W is therefore you use the very same equation, right? 2 times 11.7. This one you can refer to the table. VBI, you can get the relative permittivity value, right, in vacuum, and then you times in order to get the one for silicon. 11.7 is the relative value times 8.85 times 10 to the 14. VBI, if you've done a calculation for the VBI. For example, if you're not given any VBI value here, you can just calculate using VBI equals to VT ln NA and DN squared, just like what we did on the previous example, right? So that should give you 0.635 as your VBI over Q, the electron charge, times the whole product of your Na plus Nd over Na Nd, and then you square everything, right? And that will give you a W of 0.95 micron, okay? 0.95 micron. So whenever you've done the calculation, so make sure you convert this unit into a more appreciable unit, right? Walaupun the cm you can still appreciate, but then cm sounds big, even though it's just 10 to the minus 4. small, right? But if you convert that into 0.951 micron, it makes more sense because we have been discussing about wafer thickness of about 400 micron, 300 micron, and the depletion region width in this case, if you have your PN, for example, if you have P and N, your P is only 10 to the 16 dope, and N is 10 to the 15 dope. So therefore, that will give you depletion region of only 0.95 micron as this region. So this width in the middle, the whole stretch there in the middle is only 0.951 micron. It's not even 1 micron. So you just imagine if you are working on a silicon wafer with 200 micron, so 300 micron. So the depletion region width there is only less than 1 micron, very, very, very thin, right? If you compare to the neutral region outside. So if you compare this to this, assuming this is like 200 micron, so your depletion region width is only like 1 micron, less than 1 micron, 0.95, and the whole other region of 199 micron is on the left and on the right. The whole region of 199 micron is neutral in nature. Kat tengah tu je yang akan determine your PN junction punya properties mainly. Okay, so when you relate this into devices later on, most devices rely on this PN junction physics. For example, if you talk about solar cell, your carriers generated from the incident photons that generated free electron hole pairs, they need to be separated at the junction. So maksudnya if you're working on 200 micron silicon wafer as your solar cell, for example, this operation of your solar cell relies on the 0.95 micron width in the silicon to be able to do the rest of the operation principle. Okay, and that's the heart of the device. A very small area out of the whole other volume, if you like. Okay, so that's why the PN junction is very important. So if you don't have that junction to work properly, then in that particular case just now, you won't have your carriers to be successfully separated from each other, and they will just recombine and the device is gone. So the separation of the carriers so that they don't recombine and they can be collected on the opposite electrodes on P and on the N and complete the circuit and give you some results relies on the heart of the device operation, which is in the PN junction, as small as 0.95 micron. So yeah, so kalau if you're talking about integrated circuit of 500 micron, 700 micron, if you're talking about this doping level 10, 15, 10, 16, that means the key is only in the 0.9 micron if you're talking about these doping levels, right? Which affect the whole operation of your 500 micron devices. That's how powerful is the PN junction. Okay, is it okay so far? For PN junction and the thermal equilibrium, I'm gonna move on to bias condition. Do you have any question? I want you to try out your own calculation. Yeah, I don't have time to give you many different calculation examples because they go back to the very same equation, the very same principle. So I just would like to discuss with you the basics so that you can you know how to plug in the equation and what does it mean eventually. For example, what is the meaning of the 0.95 micron for a device operation? So I already explained now. So any question? Yep.
For the first equation, for the VBI, there's a term VT there. What does that stand for?
Right. VT is actually the thermal voltage and is given by KT over Q. As we mentioned last time in, I think, carrier transport, if I'm not mistaken, KT over Q, Boltzmann constant times the temperature of your room or whatever temperature over electronic charge. So that will give you about 26 millivolts usually, or 0.059, or you can round out to 26 millivolts.
So for in that question, it's usually given the value of VT, is it?
Yeah, usually if you're working on questions which uses the semiconductor at room temperature T 300 Kelvin, you can just use 26 millivolt as your constant, unless the T is given as 500 Kelvin, 700 Kelvin. Then you have to calculate the KT over Q again and come up with the new constant to be plugged in into your VT ln and AND squared to be able to come up with your VBI.
Okay, doctor, understood.
Right? Okay, good. Any other questions? So VT equals to KT over Q, huh? Tapi I just mentioned 26 millivolts, but assuming 300 Kelvin, huh? So if you're working on 800 Kelvin, then definitely you have to recalculate the way we did for your Fermi level calculation last time, remember? We have to recalculate the distribution of electrons and stuff, the probability of occupation, and you are working at higher temperature, and you want to compare that with lower temperature. And at that point, you have to recalculate the KT over Q to be able to come up with a new thermal voltage at the new temperature. If there is no question, then let me just move on to the new topic for the next perhaps 20 minutes. All right. Okay, can you see the slide on the screen? PN junction biased. Good, I've uploaded this on eLearn, yeah, this morning. So PN junction bias. So let's recap a few things as what we did last time. How do we form a PN junction? Anyone? How do we form a PN junction? You can unmute yourself. Such a simple question. How do you form PN junction? Anyone?
Combining a P and N semiconductor.
Yes, as simple as that. Combining a P and N semiconductors, right? Good. Second one, once a P-type and N-type semiconductor is brought into contact, what is going to happen? Yeah, by making N and P in contact. Good. Okay. Same thing. Right. Second question. Once you combine P and N into contact, what is going to happen next? Forming a PN junction, yes. Then what is going to happen next? You've got a junction there. What's next? Before the drift, diffusion first, right? So why do you have diffusion at that point? Kenapa ada diffusion? Bila you combine, due to concentration gradient, right? So electrons are going to see a huge gradient on the other side. Sebab tak ada electron. The minority carrier is very small on the other side. And the same goes for hole. Then you're going to have a presence of diffusion, concentration gradient that will induce diffusion of carriers both ways. Electrons from n-type into p-type, holes from p-type into n-type. Right? Then what's next? Once we have your diffusion, then what's next? Can you tell me a story there before you get a thermal equilibrium condition? Apa jadi? Diffusion, then what else? It has to be quite a story there before you get a PN junction, before you get a thermal equilibrium condition. Okay, positive and negative ion cores form on both sides. Okay, and then slowly form electric field, be electric field at the junction, forming a barrier, right? Forming a barrier, and as a result, further diffusion of electrons and holes is stopped. Okay, yeah, drift occurs due to the presence of electric field. You're going to get drift of the carriers as well. And as a result of the presence of the full barrier, you are going to stop the further diffusion of electrons and holes as the original condition. Okay, but then you are going to stop further diffusion of electrons from n-type into p-type. You are going to stop further diffusion of holes from p-type into n-type, and you have achieved thermal equilibrium condition. So can you explain a little bit what happens to the EF before and after thermal equilibrium? What happens to the EF before and what happens to the EF after TE condition? What was the EF like before and junction? And what is the EF like after the junction? Yes, go ahead.
Before the junction is have how to say it's like separated for n-type semiconductor it has its the EF is near the valence band, and for p-type for n-type semiconductor the EF is near the conduction bands. So once we
Okay.
make forming the junctions, there
Okay.
will be there will be a band narrow the band a new
And
band
bending.
alignment
Okay.
making the Fermi level to be same in a line, and
Uh-huh.
there will be an a narrowing, or we should call a
Bending, bending.
misalignment, a
Bending
bending,
in the
yeah, a
middle.
bending
Yep.
in the middle to form like a gap. That gap will that gap is called a barrier junction.
Very high.
Then to
Yep.
stop further diffusion.
All right. So what happens to the EF at thermal equilibrium condition? How many EF do we have at thermal equilibrium condition? One, right? So only one EF at thermal equilibrium condition. We had two EF before thermal equilibrium, right? From P-type and from N-type, eventually merge into one EF the moment TE condition is achieved, is obtained. Good. So those are the things. If you're asked about what will happen the moment you put P and N in contact as a junction, those are the stories. Diffusion, concentration gradient, diffusion, electric field, drift, EF alignment, all those stuff, and eventually thermal equilibrium condition, right? So those alone is like 5-6 different keywords already, 5-6 different points, and it will probably carry up to 30 marks in a typical exam, right? So depending on the scope, well, it can typically carry 30 marks by those stories, those poems, those flows, and of course a sketch of what happened before and after. So next, what is depletion region? What is depletion region? Anyone? Sofiuddin? Lama tengah suara. What is depletion region, Sofiuddin? How do you define that region? Najia? Najia Ramli? What is a depletion region?
A space charge region.
A space charge region. How do you have that? What happens to be able to, what has to happen in order for you to have that region?
The charge extension in the P and N region.
Okay, to be able to get that charge, what has to happen first?
Drift.
Drift, no, before that,
Diffusion.
diffusion, right? Diffusion. So you need to tell a diffusion of majority carriers from n-type into p-type for electrons, leaving fixed positive ion charges in the n, and the opposite as well, right? Leaving positive ion charges in the p, or negative ion charges in the p. So how do we then calculate the built-in voltage at the junction? Baru je discuss tadi kan? What's the
VBI.
equation? VBI equals to
VBI equal to VT ln NA ND over NI square.
Yep. All right. Good. So those are the things that you have to understand in the topic of PN junction at thermal equilibrium. So let's move on to bias. So what is bias? So bias means you want to apply external voltage to your junction. And this external voltage can come in the form of a positive voltage or negative voltage. And you can even swap the polarity of your voltage on the P and on the N. You can swap, you can make it positive here, negative there, and you can even swap negative here, positive there to be able to induce different effects, right? So PN junction under biasing condition at thermal equilibrium. So when I say at thermal equilibrium, that means there's no bias at all, or zero bias if you like, right? Potential barriers seen by electrons hold back the large concentration of electrons in the N and keeps them flowing into the P. So this is what we discussed on the stopping further diffusion of electrons and holes into the opposite region by the barrier. Okay, by the barrier QVBI. This potential barrier here is the QVBI component that we need to calculate, or we've discussed the equations now. Similarly, the potential barrier is seen by holes in order to keep flowing to the other side as well. So the potential barrier then maintains thermal equilibrium. So the barrier that you have obtained, the QVBI, will keep the thermal equilibrium condition as it is, and there's no more further diffusion of electrons into the p-type, holes into the n-type. Selagi mana you are still having diffusion of electrons into p-type, holes into n-type, so that means your thermal equilibrium condition is not yet achieved. Okay, sampai they achieve tu means there's no more diffusion, macam everything stops. Everything stops. So that is thermal equilibrium condition. And that can be equated to, okay, if you look at these three different 445, let me go for another 5 minutes perhaps, max 10 minutes max. So PN junction and its associated band diagram for A0 bias. So here the left one is thermal equilibrium condition, B reverse bias, C forward bias. So you may have one of the three conditions related to the PN junction. So tengok ke atas first, PN junction, tengok yang paling kiri first, dengan tengok yang tengah kanan lagi. So here is you have your PN junction and you have your space charge in between, you know your W, but then you have nothing acting on the system. So now the system is set to be at thermal equilibrium condition. And this is how the band diagram looks like. So we have discussed about this bending. We have discussed about this single EF at thermal equilibrium condition. We have also discussed about the formation of this QVBI thing, just like what we mentioned Q psi naught. Sama, huh? So this QVBI is the energy barrier that keeps electrons from flowing into p-type and keeps the hole from flowing into n-type. Okay, so this is what maintains the thermal equilibrium condition. Kalau you buat connection pun, you don't actually apply the bias, ataupun you just set to zero bias and basically nothing happens to the system by the bias. Okay, if you see this, okay, let's move on to the central part, the central image. You can, as I said, you can either, this is the polarity, the positive and negative polarity. You can either connect your positive to the p-type or n-type. You can swap them and induce different condition. But in this particular condition, it's called reverse bias. So look at the connection now. So the negative connection, the negative terminal is connected to p-type, and the positive terminal is connected to n-type. So we know that before this we learned that p-type, you can say that p-type is positively charged because the majority carriers are holes. You can say that n-type is negatively charged because majority carriers are electrons. So sekarang ni, when you want to do reverse biasing to the junction, you have to connect the polarity to be in opposite condition. So that means this negative terminal goes to positive material, which is p-type, and this positive terminal goes to the negative type, to a negative material. So the moment you're connecting them in reverse polarity, you call them as reverse biasing. And the voltage which controls the biasing level, the bias level, is called as reverse bias, VR, reverse bias. So what happens now what happens now to the PN junction as far as the band diagram is concerned? Kita tengok sekarang apa perubahan pada band diagram. So what happens now? You can see that, can you see the depletion region? If you compare the depletion region of the reverse bias condition to the depletion region of the thermal equilibrium, what happens to the depletion region from the image? It becomes wider, right? It becomes bigger. So the moment you apply reverse biasing on your junction, your depletion width increases. It's going to get bigger and bigger. So what happens to your band diagram? So what happens next is your Fermi level. It was originally a single EF at thermal equilibrium condition. Now the Fermi level will split. Dia akan split, dia akan pecah dua into EF in the p-type, EF in the n-type. You can label that as EFN, EFP as also labeled in the previous case. But instead of having a single Fermi level, it's now split into two, right? EFP and EFN and the VBI. What happens to the VBI? Can you see now the VBI of reverse biasing if you compare to thermal equilibrium? Apa-apa pun compare to thermal equilibrium, so that's the reference condition. Right. So your VBI increases. Your VBI now is given by VBI plus VR. Maksudnya apa jadi kat barrier height? So if you imagine yourself as electron or hole, do you see easier? Do you see higher barrier height or lower barrier height? Is it easier to cross now or harder to cross now? Or it's just the same? Okay. So imagine this VBI as your tembok nak cross. If you want to jump over, for example, yeah, it's harder to cross because you are now reverse biasing the junction. You tambah lagi barrier tu. Instead of just VBI, you're adding up to that. You're adding VR to the VBI and makes it harder. Okay. So what happens to the electrons and holes? They will be kept in the original site as in the thermal equilibrium condition. There's no way to cross. It just becomes a lot harder to cross now. It's no way easier at all. Okay. And the division width becomes wider as what we saw before. So now let's look at the third condition. So it's called forward biasing. And forward biasing is achieved when, so tengok balik polarity. So this is the tip, tip is polarity. So you are connecting the positive side of the terminal to the positive material. Positive, sambung positive, and the negative side of the terminal to the negative. Right? The moment you're doing this, same polarity, positive to positive, negative to negative, this condition is called forward biasing. And you can represent the voltage by VA. Ataupun you nak letak VF pun boleh. Either one is fine as long as you know what's the meaning. Applied voltage in this case, you can put VF as forward bias if you like. What happens to the depletion width? In a comparison to thermal equilibrium condition, what do you see? This width versus this width, right? Depletion width becomes narrower if you compare to thermal equilibrium condition. Always compare to TE condition. You don't compare dua ni boleh, but then you don't forget the middle one, the original condition. So what happens next to the band diagram? Now your band diagram is given by, okay, you will also have your Fermi level to split, no more single as in the thermal equilibrium condition, but the way it splits is different in this case because your barrier height is now, what do you see the barrier height? When you compare forward bias versus TE, right, it becomes smaller, right? It's a lot easier for the carriers to cross. So, and your effective height is now given by Q times VBI minus VA, ataupun VBI minus VF, if you like, right? To denote forward bias condition. So your barrier height originally was just VBI. Tapi sekarang bila you minus VA, so this VA will actually reduce the level of your barrier height. So you can then control or modulate your VA in order to control the barrier height. Hence, you can control the flow of the carriers right after this. Okay, to induce the flow of electrons and flow of holes across the barrier again, just like before TE was established. Remember last time we used to have diffusion of carriers, electrons into p-type, holes to n-type until you have TE, and then it stops. Now you are modulating or regulating the VA in order to play around the barrier height so that you can push the electrons to move, to diffuse into p-type again, holes to move into n-type again, and continue the diffusion process. Okay, so that's what happens. So let me just finish with this description. At reverse bias, the potential of the N region is positive with respect to P. This is the split of the EFP and EFN. The total potential barrier is now larger than that for zero bias condition. So it's now the barrier height or QV BI now becomes larger if you compare to the TE, because now VBI is given by VBI plus VR, right? It increases, and then you expect the width of the depletion region to increase as well. The increased potential barrier continues to hold back the electrons and holes on both sides. Duduk saja tak pergi mana, because it's now even harder for them to cross. It was already hard at TE, but it's now even harder, and they wouldn't be able to cross. There's still essentially no charge flow, and hence essentially no current. Tak ada current. Reverse bias, eh? So it's why reverse bias, you don't have any current. On the other hand, at forward bias, when a positive voltage is applied to the P and with respect to the N. So remember the polarity, P to the positive, no, positive to P and negative to N, and that's reverse bias. The Fermi level is now, in the P region, is now lower than that in the N region. The potential barrier is now reduced. The QVBI is now given by QVBI minus VA or VF. Either one is fine. So that essentially means the barrier is now reduced, the defective barrier. The smaller barrier means that the field in the depletion region is also reduced. You are actually opposing the presence of the electric field due to the built-in voltage earlier on. Okay, you reverse, or you try to cancel out the electric field present due to the TE condition. The smaller field means electrons and holes are no longer held back in the P and N type region respectively, and they can start crossing. There'll be a diffusion of holes from the P type across the space charge where they'll flow into the N type, and the same goes for electron as well. The flow of charge generates a current through the P-N junction. The injection of holes into the N type means that these holes are the minority carriers. So that's why it becomes important again. That's why you have to go back to the previous curve tadi kan yang saya majority crossing becomes minority. So this is the thing. The injection of holes into the N-type region, so it was originally from P-type as the majority. Injection of holes into N-type means now the holes are minority carriers, which is given by, now what is it given by? We used to discuss about PP naught, PN naught. What do you think is the notation to represent this sentence now? Injection of holes into the N-type means the holes are now the minority carriers. What do you think is the notation that we can use to denote this? Any idea before we finish? Yeah, it's called PN. No longer not, no longer not, because it's no longer at thermal equilibrium. So it now becomes PN for holes in the N-type and NP for electrons in the P-type. Remember the not, that's why I told you to always define as three things, PN naught and PP naught, NP naught, whatever. Now it's no longer under not condition. So you remove the not. So now PN naught, what's supposed to be PN naught now becomes PN. What's supposed to be NP naught now becomes NP because it's no longer under thermal equilibrium condition. Okay, so this is the thing that we essentially the thing that we summarize now from the three different conditions. QVBI, and then you forward bias, you reduce the barrier height. In your reverse bias, you increase the barrier height. Okay, so let's just stop here for today, and tomorrow we'll continue with the rest of the PN junction under bias condition. Is there any question for now?
Doctor, can I ask a question?
Yep.
Doctor, regarding the equation for finding the depletion region width, the epsilon symbol means what?
The permittivity
again,
of your material, of your silicon.
Oh, okay.
So yeah, you have to check on the relative permittivity value and times the value for the free space.
Oh, okay.
So that's why you saw is now 11.7. So now it's 11.7 times 8.85 times 10 to the minus 14. So you have to get the relative value and times the value of the free space to be able to get the value of the material, because the relative value is given by the value of the material is over the value of free space, right?
Yeah,
So,
doctor.
yes. So you have to look at the material. If you're working on silicon, then that's the value. If you're working on PN junction on gallium arsenide, for example, then you have to pick the value from gallium arsenide. Okay? So is there any other question? PN junction bias condition for now? Can everyone follow? Do you have anything that you missed or you don't understand from?
Doctor, that symbol refers to relative permittivity of that semiconductor, right?
Yes, yes, yep. And the relative value is given by the value of that material over the value in the free space, right? So we just rearrange that equation.
Yeah, I see, doctor.
Okay. So any other questions? Do you guys understand now the changes from thermal equilibrium to forward bias and reverse bias for depletion width, carrier flow, barrier height, band diagrams? You should be able to draw the band diagrams, yeah, for all the three conditions and describe the flow of the carriers, barrier height, and so on and so forth. Any question for now? Better? So hopefully in the next session we can do some calculation related to the minority versus majority, not under thermal equilibrium condition. So we're talking about Pn and P without the not, right? In comparison to the value in the not in the thermal equilibrium condition. So it's going to be a bit confusing, but if you understand the meaning of the Pn naught, NP, MP naught, PP naught, and the equation we talked just now, Pn naught equals to PP naught exponential of whatever. So those will be handy. That's why I always stress about the three things. You have to be able to define the PP naught, Pn naught, because if you are able to define, then when you move to bias condition, you can just remove the naught. Then you still understand the thing. Tapi kalau tiga benda tu you are not able to tell yourself, then when you move to the bias condition, it's going to be a bit confusing or a bit messy, right? So get that back on track to make sure you understand the thermal equilibrium condition first before you move into biasing or some other conditions. Okay, so kalau ada soalan, I'll see you tomorrow then. Bye bye, take care, assalamualaikum.